welcome to this last section of this course, and in this particular lecture and in the coming 2 to 3 lectures, what we are going to do is we are going to see the finite element formulation of ductile fracture in coupled thermoelastoplastic dynamic contact problem. Okay. So, in our previous discussion, the constitutive model that we had taken was for a compressible hyperelastic material, okay, which was neo-Hookean material. Okay. So, now that is a very special kind of material, which is where you can derive the stresses from the stored strain energy density potential. Okay. So, there was no dissipation involved, and as such it led to a very convenient and easily implementable finite element form. Okay. So, we had derived till Newton-Raphson procedure in our previous lecture. So, now to give you an idea and glimpse of the application of continuum mechanics in the computational setting, I have taken this complete formulation of coupled thermoelastoplastic dynamic contact problem, where you have to simulate ductile fracture. Okay. So, it will be a very concise presentation, in a sense that I am not going into deep into each and every aspect, but the idea of this whole presentation, okay, in the coming lectures is to show you that if you can identify the physics of the problem, you can actually simulate a lot of complicated problems, okay, involving dynamic effects, thermal effect, contact, okay, plasticity, and on top of that the behavior of the material degradation, okay, because of the cracks that originate inside the body because of the loading that it is subjected to. Okay. So, the title of our presentation, okay, is the finite element formulation of ductile fracture in coupled thermoelastoplastic dynamic contact problems. Okay. So, our plan for the next few lectures is as follows. Okay. So, we will first have a brief introduction, followed by, in the present lecture, we will discuss what is actually meant by damage. Okay. So, after that, in the next 2 lectures, we will see the mathematical modeling of a damage coupled large deformation dynamic thermoelastoplastic contact problem. Okay. So, here it will be a mathematical model where we will have the effect of the damage. Okay. So, the degradation of the material performance because of the voids, the cracks that form inside the body. The body will be allowed to undergo large deformation, which means the strains will be very high, okay, which is generally found when the body undergoes severe loading, where the loading takes it beyond the yield limit. Okay. And in this course, we will deal with ductile material only. I mean, in this particular discussion that we are going to do, we will also consider the effect of time. Okay. Till now, we did not consider the effect of time, but now we will bring in the effect of time also, where the inertia terms, mass into acceleration, become important. Okay. Then we will also bring in thermal effects. Okay. So, you can read here, it is called thermo. Thermal effect means when the body is getting deformed. So, the plastic work that is being dissipated. Okay. So, body is getting plastically deformed. So, the plastic work associated with this plastic strain, okay, gets released in the form of heat inside the body. Okay. So, that heat also affects the deformation, and also when the two bodies contact each other, because this is a contact problem. So, because of the friction which happens between the two surfaces of the contacting body, there will be frictional heat which is generated. So, a part of the heat goes inside one body and part of the heat goes inside another body. So, this heat also affects the deformation, at least at the local level, where at the near to the contact surface. And then our material will be elastoplastic, which means the material is allowed to deform beyond the elastic limit. It can deform plastically. So, you see we have one physics which is damage, we have another physics which is time, we have another physics which is thermal effect, thermo, and then we have elastoplastic. So, in all we have 4 different physics which come into this particular problem. So, there is this multi-physics problem. So, once we have developed the mathematical model for this damage coupled large deformation dynamic thermal elastoplastic contact problem, then what we will get is a equation which is similar to the Newton's second law. So, now to solve that, so that will be finally we will derive the weak form, and then that weak form has to be converted to the finite element form. So, there will be time involved. So, we have to do what is called the finite difference formulation in time. So, in space we will do finite element formulation, and in time we will do finite difference formulation. So, we will use Newmark's time integration scheme for finite difference formulation. So, we will also do the thermal formulation. So, we have to take into account the plastic work and the frictional heat which is generated, and top of that we will also consider whether some outside heat is also coming inside the body. So, with taking all this into account, we will develop our thermal formulation to find out the temperature T. And then because it is a contact problem, we have to carry out the contact formulation, so that we can ensure that one body which is impacting the another body should not go inside the another body. So, for this we will use what is called the Lagrange multiplier method. We will use Lagrange multiplier method. And once when we develop a formulation from step 3 to step 6, we have our formulation. If we have developed our formulation, we have developed the mathematical formulation, we have discretized in space and time here, and then once we have discretized everything and we have developed our finite element formulation, we go and implement that finite element formulation inside a computer code, and we develop a computer code which first needs to be validated. So, we will see how do we do the validation. So, the purpose of this is to show the steps when you yourself will write any formulation, develop any code, and based on some formulation that you have developed, in that case you will first have to do the validation of your problem. Validation means you take some examples from the literature which are already available, which can be done using the formulation that you have developed in your code, and then you run those problems using your own code, and you match your results with the results that are reported in the literature for that particular problem. It can be an analytical problem, like for example, Hertzian contact, for which an analytical solution is available, or it might be some experimental results which people have already done, or it might be the numerical result or the finite element results of somebody else. So, you take those problems, you solve using your own code, and you see how good your code matches, results of your code matches with the results of the literature. Once you have done this and you are satisfied with your results, that is you have completed your validation, then we will see some of the results that we have obtained using our formulation that we have developed from step 3 to 6. And finally, I will conclude this course with some concluding remarks, what we have done in this course and what we have left in this course. And if you want to go into detail about various aspects about this course, then where to look for suitable literature. Okay. So, with this we first see that in the last part of this course we had shed some light into the formulation and simulation of fracture in coupled and thermoelastoplastic coupled problem. Okay. So, I will say that in this part of the course. Okay. So, this part of the course we will shed some light into the formulation and simulation of ductile fracture in coupled thermoelastoplastic contact problem. Okay. Now, fracture, as you all would know, okay. So, we come across fracture in almost our day to day life very often. Okay. So, some of the fracture types are inconsequential type, okay, and some can be consequential in nature. Okay. So, inconsequential fracture are, for example, breaking of a china dish or pencil leads, glass of a window, okay, tearing a notch lid of a cola can. Okay. All these kind of problems where you have a fracture. Okay. So, the dish breaks and there are a crack which is generated and your dish is broken into multiple pieces, or a pencil lead, when you apply a lot of pressure beyond a certain limit the lead breaks. Okay. So, all these kind of fracture do not have any severe consequence on your day to day life. Okay. So, if your dish is broken, you will buy a new dish. A pencil lead is broken, you will sharpen again. If a glass of a window is broken, you will replace it with a new glass. Okay. And of course, the cola can, once you have completed the drinking the cola can, you will throw that in the dustbin. Okay. So, these are some of the day to day inconsequential fracture problem that we come across. Okay. So, we do not often study that. Of course, I mean, designing a china dish which will not break, or a pencil lead which will not break till a certain limit, okay, or a glass window which is much more resistant to certain kind of impact. I mean, these are can be studied, but from our point of view these are not that much important, and we classify them into what is called the inconsequential type of fracture. Okay. Now, however, if you have fracture of a cup during the drawing operation, okay, or you have a armor penetration of tanks, or crash worthiness of automobile, or the grounding of ships, tearing of pipelines, or the rigidity or the tearing of aircraft fuselage because of the cracks that might occur, okay, in the fuselage, are some of the examples where fracture is often accompanied by huge economic loss, and it also may lead to loss of the human life. Okay. So, there are these kind of problem. Okay. So, for example, armor penetration of tank. So, if you have not designed the armor of a tank very properly, then the shell, the anti-armor shell may penetrate the armor of the tank and may explode inside the tank, causing severe casualties for the tank crew. Okay. Similarly, a car for which the crash worthiness has not been carried out properly may lead to the severe injury of the occupants of the car. If there is an impact, head on impact or side on impact, okay, it may lead to casualty. Okay. And then this grounding of ship, okay, so the hull of the ship, if the ship is grounded, okay, it touches the sea floor and it might happen, then the cracks appear in the hull, and if the ship is carrying some nasty kind of chemical like petroleum, it may spill and cause a lot of problem. Okay. And then the petroleum pipelines, okay, the tearing of pipelines, okay, are used all over the industry. They carry a lot of harmful combustible substances like gases or petroleum, and under the action of certain kind of loading, if there is an earthquake or if there is a thermal load or something like this, and there is a tearing of these pipelines, it also leads to a lot of economic losses and sometimes huge loss of human life. Okay. So, also aircraft fuselage, aircraft goes, so an airplane goes up in the air. Okay. So, it goes from atmospheric pressure where it is, the cabin is depressurized, it goes up where it is pressurized, it comes down, lands, it is again depressurized, and the same cycle goes on and on for many times, and then this kind of loading, that is this kind of fatigue loading which is there, may cause problem in the fuselage. And nowadays what happens with a lot of companies focusing on thinner and thinner material, trying to reduce the weight of the aircraft. Okay. So, the fuselage is very critical for the safe performance of the aircraft. Okay. So, if fuselage breaks mid-air, then there is certainly loss of human life is involved. Okay. So, these type of fracture is what we call the consequential types of fracture. There is certain economic consequence or human life loss as a consequence of these kind of fracture. So, these kind of fracture is what we see in this last part of this course. Okay. So, we in this discussion we focus on the second type and concentrate on its simulation for few test cases. Okay. So, we are not going to discuss how to simulate the armor penetration or aircraft fuselage or something like this, but the class of problem that we will do will have a similar kind of fracture which occurs in these kind of problem. Of course, if you want to write a code for these kind of problem, it is going to be a very messy job, and already there are commercial packages which are available which can do it for you. Okay. So, with this we move to the question of damage. Okay. So, in this particular formulation that we are going to discuss, the fracture is incorporated through what is called the damage mechanics approach. Okay. So, there is material which is said to be damaged because of the loading which occurs on the material. Okay. So, material is acted upon by different kind of load, dynamic load, external load, thermal load, and because of that the material loses its load carrying capacity. So, this loss of load carrying capacity is what we call as damage. So, we say the material is damaged, that is it cannot bear as much load, okay, as it could before the loads were applied. Okay. So, before the loads were applied, suppose the material could take 100 Newton, but after the loads are applied, there are cracks and all that form inside the body, and the overall strength carrying capacity of the material goes down from say 100 Newton so to 80 Newton. Okay. So, you cannot go to 100 now, you have to go till 80 only. Okay. So, fracture was initially analyzed using linear elastic fracture mechanics approach. Okay. And later on using the elastoplastic fracture mechanics approach. Okay. So, the linear elastic fracture mechanics is called LEFM. This is still very popular, where we find the stress intensity factor, J integral, and all these kind of concepts are there. Okay. So, however, in 1958, okay, so Professor L.M. Koshnov proposed a simple model of material damage which has since been extended by many researchers like Lemaitre and Desmora, Murakami, to brittle, plastic and viscoelastic or viscoplastic material. Okay. Now, Professor Koshnov suggested that there is something called damage, and with this damage you can analyze brittle, plastic or viscous kind of material, fracture in these kind of materials. Okay. So, this particular model has now evolved into a new field which is called the continuum damage mechanics field. Okay. So, there is a whole journal of International Journal of Damage Mechanics which caters to this field of continuum damage mechanics. Okay. So, the models based on continuum damage mechanics can not only analyze, but also predict failure of materials through evolution of internal damage before external micro cracks are visible. Okay. So, in linear elastic fracture mechanics and all, okay, there has to be a crack already present inside the body, and then you analyze when can the crack grow and in which direction it can grow, okay, whether at all it can grow. But here in continuum damage mechanics, there is no such restriction that there has to be a crack. Okay. So, it can not only lead to the prediction of failure of material, but it can also predict the evolution of the damage. So, from no damage inside the material to complete damage, the whole path of fracture can be done using the field of continuum damage mechanics. Okay. Now, there are some well known examples of failure of real life structures. Okay. So, it is interesting to see how the failure to understand the correct response of the material to different cases, okay, has led to severe failure of real life structures in past. Okay. So, one of the most famous example is the failure of the Titanic ship. Okay. So, as you know, in 1911 Titanic ship was going from UK to America, and over the Atlantic Ocean it collided with an iceberg which caused a tearing of the underside of the ship, through which water entered inside the ship, and then it eventually sank Titanic. Okay. Now, what caused this fracture? Okay. So, obviously, you see there was this iceberg which tore through the steel plates, okay, which formed the outer covering of the ship. Now, later on it was found out that the steel which was used, okay, so under test condition the steel was very ductile, okay, which means that it would deform, but to cause a failure it took a lot of effort. But then when it was floating in a ocean where the temperature was very low, then the behavior of the steel changed from ductile to say a lower level of ductile, closer to the brittle nature. Okay. So, when there was a huge force which was applied through that iceberg, that steel plate, instead of undergoing large plastic deformation, it immediately cracked, okay, which caused the failure of the outer hull, and then through which the water entered, leading to the eventual sinking of the ship. Okay. Also, United States launched a lot of ships called the Liberty ships during World War II. So, close to 2,500 ships were made, and these ships were rapidly made, and these ships were used to carry armaments and all those kind of stuff during World War II. And because of the sheer pace at which they were built, there was no time to study the behavior of the metal which was being used to make those ships under very cold condition. Okay. So, close to like 40% of these ships sank because of the similar kind of failure which was seen in Titanic. Okay. So, when they entered very cold water, the outer metal of the ship became very brittle, and then it led to the failure of the ship. The complete ship would crack into half and then sink. Okay. Another very famous example is the failure of the de Havilland Comet passenger aircraft in 1950s. Okay. So, this failure has led to the rise of American companies in the passenger aircraft field, for example, Boeing, and which continues to this date. Okay. So, de Havilland aircraft were the first jet engine aircraft, and they would manufactured in UK, and they will actually fly from one place to another, and then what happened was, in the fuselage all the windows were of this particular shape. So, they had sharp corners. Okay. So, few of the aircrafts, when they were operating, they cracked into half in mid flight, leading to the crash of the aircraft, and all the passenger lives were lost. Later on, when the problem was studied, they were found that due to the continuous pressurization and depressurization of the cabin, there was this fatigue loading which was being exerted on the fuselage and also the windows, and these sharp corners were where a crack would originate, okay, because there was the sharp corner, and then because of the sharp corner there was a stress concentration, and the cracks would originate at those sharp corners, and then after a certain number of loading cycles there was a catastrophic propagation of this crack from one window to another and also over the fuselage, leading to breaking of the fuselage into two parts and eventual crash. Okay. So, when this was found out, till that time Boeing had started making windows which were like of this shape. Okay. So, there was no sharp corner, there was a blunt corner, okay, which led to stress relaxation, and stress would not concentrate, and leading to much better performance of the aircraft. Okay. Also, another famous example is the failure of Space Shuttle Challenger in January 1986, because of the failure of the rubber of the O-rings which are there in the rocket. Okay. So, the O-rings are which made of rubber, and they are there to, there are two sets of O-rings which are there to protect the leakage of fuel from the booster of the rocket. But in January 1986, when the shuttle was launched, that day the temperature was very low, something like 4° centigrade, and at this temperature the rubber rings, okay, that is the O-rings which are made of rubber, they became very brittle. Okay. So, there was a transition of material which was ductile from ductile to brittle, which caused the catastrophic failure of these O-rings, which led to the escape of hot gases and fuels which mix, eventually leading to the blast of the Challenger, and all 7 lives were lost. All the astronauts were lost, along with a young teacher who was also going into the space for the first time. Okay. So, that were some real life example where failure to appropriately study the nature of fracture has led to catastrophic failure. Okay. So, that is why studying the response of the material under different loading conditions is very important. Okay. Now, fracture can be classified into what is called the ductile fracture, the brittle fracture, creep fracture, fatigue fracture, and spallation. Okay. So, although these three can be categorized into either of these two, we have kept them separate and we just call them 5 different cases. Okay. So, ductile fracture is when the nucleation of micro voids and micro cracks and subsequent collisions occurs after appreciable plastic deformation. Okay. So, the material undergoes a lot of plastic deformation before the body generates some micro voids or micro cracks inside it, okay, which leads to the ultimate fracture. Okay. So, in this, the damage or the fracture is called the ductile fracture, and then the plastic strain in ductile fracture goes above a threshold value. Okay. So, these kind of fracture usually occurs in materials like mild steel, aluminum, copper, etc. Okay. So, this figure over here shows the graph of a stress strain graph of a typical ductile material. Okay. So, when you load a ductile material, it deforms elastically till a certain point called the proportional limit, after which it reaches the elastic limit, and then at this point the material yields. Okay. So, this is called the upper yield limit and there is a lower yield limit, and and if you keep on applying the load, the stress again increases when it reaches a maximum point called the ultimate stress, and finally, there is stress concentration and a lot of cracks and all coalesce together. Okay. So, the voids and cracks start forming after yielding, but after ultimate point they start coalescing together with each other, resulting in the failure at point R. So, there is a, you can see after the yielding has started, still there is a considerable deformation which happens before the eventual fracture takes place. Okay. Now, the second type is called the brittle fracture, where the nucleation of micro voids and micro cracks and subsequent collisions occurs without appreciable amount of plastic deformation, okay, and the damage is categorized as brittle fracture. Okay. So, this type of fracture is usually observed in concrete, glass, ceramics, composites, cast iron, etc. Okay. So, there is no appreciable plastic deformation which occurs, and the failure is mostly by debonding. Okay. So, you see the plot of the stress strain curve of a brittle fracture. So, there is elastic deformation, and immediately after plastic deformation, the material, a small amount of plastic deformation, the material fails. So, there is no considerable plastic deformation in brittle fracture. Okay. Now, we quickly look into what is meant by creep fracture. Okay. So, creep fracture is sometimes the plastic deformation is accompanied by viscous effect. Okay. So, in creep fracture you have to take into account viscous effect, and in fatigue fracture the material is subjected to cyclic loading. Okay. So, just like an aircraft which is pressurized when it is up in the air and depressurized when it lands, this kind of loading is called the cyclic loading, and then the failure associated with such kind of loading is called the fatigue failure. Okay. Finally, spallation is when the material is subjected to impact load, micro voids and micro cracks may be nucleated by the interaction of stress wave. Okay. So, in spallation the material is subjected to dynamic loading, and because of the dynamic loading there is stress waves which are generated inside the body, and these stress waves go back and forth inside the body. They are reflected from the free surfaces and the surfaces where it is held as tensile or compressive wave, and these waves when they interact with each other, they lead to the creation of micro voids and micro cracks. Okay. So, the initial impact creates stress waves which travel through the material, and these stress waves get reflected from the boundaries and then they interfere with each other. This causes zones of tensile and compressive loading, and afterwards the reflection and interaction of these waves from various boundaries lead to micro void and micro crack nucleation, which may later coalesce to form micro crack. Okay. So, this kind of fracture is called a spallation kind of fracture. Okay. So, this is when you a body is hit by a load which is changing rapidly in time, then there will be stress waves, and these stress waves will interact with each other, creating to fracture. Okay. So, there are two approaches to study fracture problem. The first approach is the global approach. Okay. So, in this approach we have what is called the linear elastic fracture mechanics approach, where the concepts of J integral, crack tip opening displacement, crack tip opening angle, etc. are considered. Okay. So, these all fall into the area of global approach, and also we have what is called the local approach or the continuum mechanics approach. Okay. So, in the continuum mechanics approach we have continuum damage mechanics based models and cohesive zone models. Okay. So, in local approach the effect of displacement discontinuities, that is the micro voids and micro cracks, is modeled within the framework of continuum mechanics. So, we have already discussed in this course some part of continuum mechanics, though we did not discuss the thermodynamic part and the constitutive relations part that extensively, but in a pure course on continuum mechanics you would actually go through those parts which are needed to model the continuum damage mechanics or the cohesive zone models. Okay. Now, there are certain limitations which are associated with the global and local approaches of ductile fracture. Okay. So, in the global approach you can only model a small number of cracks, okay, and hence it is useful for modeling only after the macro cracks have been already formed. Okay. Now, there are some specific limitations of the global approach, which are that it can only be applied to bodies with pre-existing cracks. It cannot be used for crack initiation and propagation, although now you can combine it with XFEM kind of approaches, where you can have the crack propagation, but mostly it is limited to 2D and very difficult to do in 3D. So, parameters like J integral are not an intrinsic material property. This means that the value of the J integral depends strongly on the geometry of the specimen which is used. Okay. So, that is the problem. As you change the geometry of the problem, the J integral also changes. Okay. So, it is not a property of the intrinsic property of the material. So, this global approach can be applied only to simple geometries. Now, alternative approaches like crack tip opening displacement or crack tip opening angle too suffer from similar limitations. Okay. So, in the numerical setting, in finite element analysis, the results using J integral, CTOD, CTOA are highly mesh dependent and overestimate the crack areas. Okay. Now, there are advanced techniques like XFEM that are still mostly used for two-dimensional cases involving elastic solids or small scale plastic deformation. Okay. Now, in the local approach or the continuum damage mechanics approach, which is what we will use in the formulation that will present, the material degradation of the body is modeled. Okay. So, you will explicitly model the material degradation, which is not considered inside the global approach. Okay. And then we will analyze the behavior of the material. Okay. So, the body may or may not have initial crack, that is, it may or may not be damaged from the start. So, the cracks are modeled by smearing them out continuously at various location and at various length scale. Okay. So, as the deformation progresses, you will have certain criteria which will originate new cracks, okay, where there was no crack initially present. Now, since local approach is based on the framework of continuum mechanics, it is easier to implement inside numerical setting, for example, in usual finite element codes. So, if you have already an existing nonlinear FEM code which can model dynamic elastoplastic behavior, then it is not very difficult to incorporate the continuum damage mechanics approach. Rather, it is very simple to do it. Okay. Now, some of the specific limitations of local approach are as follows. The issue of mesh dependent result still remains. Okay. So, you can see the book by Murakami for a detailed discussion on this and other issues associated with the local approach. Okay. Also, depending on the continuum damage mechanics model used, the number of material parameters required might be too large and might be too difficult to obtain all of them from the experiment. Okay. So, now to model this damage, you have to have a damage growth law. Okay. We will see next how to get this damage growth law for a material, and there are certain constants, and these constants have to be found out using experiments. Okay. And now, in many cases, the number of constants are so large that it is very difficult to do experiments on them, and then you may have to drop some of the constants and you have to go for very simple model, which may not then truly reflect the behavior of the material under the different loading condition. Okay. So, now what is ductile fracture? Because in this particular 2-3 lectures we are discussing ductile fracture. So, now ductile fracture is what a kind of fracture where we have considerable elastoplastic deformation before the actual body fractures. Okay. So, now ductile fracture happens in 3 stages. There is one what is called the void nucleation initiation, there is void nucleation or initiation, there is void growth, and there is void collisions. Okay. So, what is meant by these? You can see in this particular image. Okay. So, let us say this shows you the secondary particles. So, inside a material there might be some secondary impurities which might be present. These are particles which are of different material than the actual material. So, the bulk material may be you may say it is iron, and the secondary particle might be say some impurities. Okay. So, this represent the voids, okay, and the cracks are represented by following figure. Okay. So, when you have a body in initial configuration, okay, so let us say this is your body or part of body and this is the initial configuration, and when you apply loads on the body, then so you have voids. Okay. So, you have for example, voids, you have these secondary particles and you may have some cracks. Okay. So, cracks, particles, they all may be oriented in different direction, they may have different shapes, although I have shown here with the same shape, they may have different shapes and different orientation. Okay. And we are seeing for the simplicity in 2D, but this can well extend in 3D. Now, as you apply the loads, the voids, the cracks and the particles will be subjected to different loads. Some of them may be tensile, some of them may be in compression. Okay. So, like this here is compression, this might here be in tension. Okay. Now, what happens once you apply the load and you increase the load, what will happen is these voids which are there, okay, or these cracks which are there, they will grow. Okay. So, the size of the crack, okay, although the ends will not grow, but the size of the crack or the voids will grow. So, this is called the void growth phase. Okay. So, also at this point you will not have any new voids right now coming into picture. So, as you keep on increasing the load, what will happen? Your size of the voids will grow to a large amount, and also new voids, okay, as you can see here, there is a delamination between the bulk material and the secondary particle which has created this kind of new surface, or the secondary particle, because the under of the action of the force may break into two parts and it may create a new set of void. Okay. So, you may have void which may form because of decohesion, or you may have void which can form because of particle cracking. So, now you have new voids. Okay. So, earlier the voids were growing, now you have new voids which have come up. Okay. And under sustained loading, okay, say you keep on applying the load, okay, then what can happen is these cracks, okay, so this crack may collides with this decohesion, this crack may collides with this particle crack, it may collides with this particular void, it may collides with this particular void here, okay, and this may grow on this side, so leading to a big micro crack. Okay. So, the collisions of micro voids and micro cracks lead to the formation of this bigger crack over here, and this is called the macro crack. Okay. So, that shows you how the ductile fracture actually happens. Okay. So, from small voids and cracks, a bigger crack may appear. Okay. And these bigger cracks may collides together. So, this might be one crack in one part of the body, this may collides with another macro crack in another part of the body to form a much bigger crack, and these much bigger cracks may reflect themselves upon the visual eyes of the person. Okay. So, it might actually be visible at the body itself, okay, then which can be detected using either visual inspection or using some techniques like ultrasonic testing. Okay. Now, as stated earlier, ductile fracture involves three stages: void nucleation, void growth and void collisions to form a micro crack, and it is found from experiments that macroscopic material properties change due to void growth. Okay. So, as a result, the constitutive relation needs to be changed when the extent of void growth is large. For example, if you have the void growth is more than 10%, then you need to account the effect of void growth on the constitutive relation. Okay. Thus, any realistic model for the prediction of ductile fracture should include the void growth dependent constitutive relation and a condition for void collisions. Okay, so, the two most commonly used macroscopic models employed to predict the ductile fracture initiation, that is micro crack initiation on the basis of void nucleation, growth and collisions are the porous plasticity model of Berg and Gurson. Okay. It is called the Gurson's model or the Gurson's-Tvergaard Needleman model, which is in short is very popularly known as GTN model. Okay. And there is continuum damage mechanics model. Okay. This is from the original work of Lemaitre, okay, or Lemaitre and Chevauche, and you can see some of the references where it has been discussed. So, it first came in 1984 within the framework of continuum mechanics, and it is called the continuum damage mechanics model. Okay. So, there are two macroscopic models which are employed to predict ductile fracture, porous plasticity model and the continuum damage mechanics model. And in our discussion, we will concentrate on the continuum damage mechanics models. Okay. So, in the first approach, which is based on the Berg's theory of dilatational plasticity, Gurson proposed a plastic potential in terms of porosity or void volume fraction, and the void growth dependent elastoplastic constitutive relation is obtained from this particular plastic potential. Okay. So, an evolution law for the porosity which incorporates both the void nucleation as well as void growth is needed when you are using the Berg and Gurson's model, and the critical value of the porosity or the void volume fraction is normally used as an indicator to fracture, okay, indicator for fracture initiation in the Berg and Gurson model. Okay. Now, in continuum damage mechanics model, the change in the material behavior is due to the void growth, and it is incorporated by introducing a new variable which is called the damage variable. In our coming slides, we will see what is meant by this damage variable, which is an internal variable in the plastic potential. So, this damage variable quantifies the intensity of the micro cracks, and as a result is it identified as the void volume fraction. Now, for isotropic damage, this can be treated to be related to the area void fraction. Okay. So, the theory of continuum thermodynamics is used to derive the void growth dependent constitutive relation and the damage growth law. Now, in our course we have not discussed this continuum thermodynamics, but this concept of continuum thermodynamics is needed to derive a thermodynamically consistent void growth dependent constitutive relation and the damage growth law. So, you can see these references over here for your reference. And now, a critical value of the damage variable which is called DCR, D critical, based either on an appropriate void collision model or determined experimentally is used for predicting the fracture initiation. So, once the damage D, okay, so this quantity damage variable which is denoted by D, when this quantity becomes greater than D critical, greater than or equal to D critical, then we say the body has failed at that particular point. There is a full macro crack which has originated. Okay. So, damage variable D, okay, is defined as follows. So, the effect of void growth on material behavior is incorporated by introducing an additional internal variable called the damage variable, which is denoted as D, which quantifies the intensity of the voids. If it is assumed that the voids are scattered in an isotropic way, then this variable can be assumed as a scalar quantity, although people have used it as a tensor quantity also, and this is denoted by D in the literature. Okay. So, the damage variable is identified as an area void fraction at a point in a plane. So, you have a body and then you cut using a certain plane, and on that particular plane you count what is the area of the voids, and then you find out the area of that plane, and then the damage variable is nothing but is the limiting value of the ratio of the voids, area of the voids divided by area of the infinitesimal area around that point in some plane. Okay. So, delta AV is the area of void traces in the plane contained in delta A. Okay. Now, the concept of equivalent stress and principle of strain equivalence is usually used during the derivation of damage growth law. And what is the effective stress concept? The introduction of the damage variable leads to the concept of effective stress, that is the stress calculated over the effective area. Okay. So, when the body is damaged, the part where you have voids or the cracks, those parts will not contribute to the load carrying capacity. So, the effective load will be carried by the remaining area. So, the total area is delta A and the area of the voids is delta V. So, the area which carries the load is nothing but delta A minus delta AV. Okay. So, this area is what actually resists the forces. Thus, the effective Cauchy stress tensor at a point is defined as sigma star equal to sigma divided by 1 minus d. So, you notice that when d is equal to 0, when the body does not have any damage, it is free of any void, then the effective stress is equal to sigma itself. Okay. And when d equal to 1, you will see a known value divided by 0, which means infinity, which means that at the tip of the crack, okay, when the crack occurs, stress goes to a very high value. So, in general it will not go to infinity. So, we will usually set d cannot cross a critical value. So, when d reaches a critical value, what we will do? We will say that our body has failed. Okay. So, this means that the effective stress, okay, total stress is actually carried out by this much area which is able to resist the load. Okay. Now, the principle of strain equivalence is another important concept, and this states that the deformation behavior of a damaged material can be represented by the constitutive laws of the virgin material if the usual stress is replaced by the effective stress, and this concept is represented in this figure over here. Okay. So, if you have a real material which is damaged and this is the actual stress sigma, then the behavior of this material, okay, the deformation behavior of this damaged material can be represented by the constitutive laws of a virgin material. Virgin means there are no voids, there are no cracks, there are no secondary particles, and then the behavior of this virgin material is same, considered same to be that of the damaged material if I replace sigma by sigma star, which is nothing but this effective stress tensor. Okay. So, then the behavior of this material, damaged material, is same as the behavior of this virgin material. Okay. So, I just have to replace sigma by sigma star and then I will have the similar behavior. So, this is called the principle of strain equivalence. Now, the specific free energy of a thermoelastic process in a damaged material can be obtained using the principle of strain equivalence as follows: psi equal to 1 by 2 rho Cij KL epsilon Ij epsilon KL, and this L over here denotes the logarithmic strain into 1 minus d minus T into S, where S is the specific entropy, okay, and T is the temperature, because we have coupled thermomechanical problem. Okay. Now, and this we get from continuum thermodynamics. So, we just straight away mention this, and now in thermoelastic elastoplastic process, the elastic strain can be obtained from the total strain. Okay. So, epsilon, so elastic strain can be obtained from the total strain as following. Okay. So, you have to subtract the thermal strain from the total strain to get the elastic strain. Okay. Here alpha is the coefficient of thermal expansion and T minus T0 is the temperature rise and delta is the Kronecker delta. Okay. Now, the Cauchy stress can then be obtained as rho into del psi by del epsilon E I j, okay, and this gives you sigma I j as Cij KL epsilon KL into 1 minus d. Okay. So, if you take 1 minus d on the other side, yours Cij KL epsilon KL becomes sigma star Ij. Okay. So, this is the, so this relation is for a virgin material, you should remember. So, sigma star is your effective stress and that is what is your strain equivalence theorem. Okay. So, the conservative part of the thermodynamic force corresponding to the damage variable d. Okay. So, the conservative part of the so the force corresponding to strain is stress. Similarly, the conservative part of the thermodynamic force y corresponding to damage is identified as y equal to rho times del psi by del d, which gives me minus 1 by 2 Cij KL epsilon Ij epsilon KL. Okay. Now, because this force, internal force is a dissipative, because damage causes dissipation, then I take the counterpart of y, which is minus y, as the dissipative counterpart of y, and this is equal to 1 by 2 Cij KL epsilon ij epsilon KL. Okay. Now, after some steps, I can show that this dissipative part of y can be written in following form, okay, where sigma dash is the divateric part of the Cauchy stress and sigma m is the mean stress 1 by 3 sigma kk, and E and nu are the Young's modulus and the Poisson's ratio of the material. Okay. And using the concept of equivalent stress, okay, I can write minus y, okay, the dissipative part of y as sigma equivalent square divided by 2 into 1 minus d square into this function, and this function can be written as function of sigma m by sigma equivalent, where sigma ratio of sigma m, the mean stress by equivalent stress, is called triaxiality. Okay. This is a very important parameter in ductile fracture, which is called the triaxiality, and then the value of this triaxiality is 1 by 3 for tension. Okay. For uniform simple tension, this value is minus 1 by 3. Okay. Now, we can also write, if I write this as f, then the dissipative part of y is written as following equation, that is equation 10. Now, I identify from the concept of effective stress this term over here, I can write this as sigma star equivalent. Okay. This is the equivalent stress corresponding to the virgin material, and then my dissipative part becomes sigma equivalent square divided by 2E into function of triaxiality. Okay. Here the expression for equivalent stress of the virgin material is root over 3 by 2 sigma dash ij of the divateric okay, of the effective stress. Okay. So, sigma dash ij star is nothing but the divateric part of the effective stress sigma ij star. Okay. Now, the constitutive relation for a thermoelastoplastic process in the damaged material can be obtained as follows. So, the constitutive equation for the thermoelastoplastic behavior of a damaged material are derived from an appropriate plastic potential F. It is assumed that in metal plasticity, it is possible to decompose F into two parts, one which is the plastic potential associated with the damage and one which is F1. Okay. Now, Fd is the plastic potential associated with damage such that it reduces to 0 whenever d is equal to 0. And now, for a material which is yielding, because according to the von Mises yield criteria, there are different yield criteria, we are using von Mises yield criteria here. The form of F1 is given by sigma equivalent minus r upon 1 minus d minus sigma y 0. Okay. Now, I can write sigma equivalent upon 1 minus d as sigma star, and I can write the yield stress as sigma y 0 plus r upon 1 minus d. Here sigma 0 y, okay, is the initial yield stress of the material in tension, and when you have 0 damage, F1 reduces to its original form due to von Mises. Okay. So, with this, the plastic flow rule then can be written as following equation, where we have to find out this lambda star. Okay. So, here, okay, from equation number 15, which is here, and this P, which can be identified with the equivalent plastic strain inside the body given by integral from 0 to 2 0 to t integration of epsilon dot equivalent plastic into dt, we can obtain the value of lambda dot as 1 minus d into epsilon dot equivalent plastic. Remember, when d equal to 0 in plasticity, lambda dot will come out. So, if damage is equal to 0, lambda dot will be epsilon dot p equivalent plastic. Okay. So, in your traditional plasticity course, this is what you will get, but when a material is damaged, that is, it has some damage, lambda dot will come out to be 1 minus d time epsilon dot equivalent plastic. Okay. Now, if we substitute equation number 17 in equation 14 and equation number 15, this lambda dots, then we can obtain the constitutive relations, that is the stress strain relation and the damage growth law as follows. Okay. So, this is the constitutive relation, it is epsilon dot PL I j equal to 3 by 2 epsilon dot PL equivalent divided by sigma equivalent into sigma dash, and the damage growth d dot is 1 minus d into the rate of equivalent plastic strain into the differentiation of the dissipative part of the plastic potential with respect to the dissipative part of the thermodynamic force corresponding to damage d. Okay. Now, this stress strain relation is not convenient for the updated Lagrangian formulation, and we will see what is meant by this, for which the incremental stress strain relation is needed. So, it is derived in mathematical modeling starting with the expression 13 for the plastic potential. Now, F1 is well established in the literature, however, FD is not well established in the literature. So, some people have suggested the form of FD. As a result, instead of directly using equation 19, so what was equation 19? This was equation 19. So, because FD is not known, so what we usually do is instead of using equation 19 for the damage growth law, experimental results for void growth measurement at different deformation levels are used to propose the damage growth law. Okay. For example, in the discussion that we have, we use the experimental results of Leroy et al. For the spheroidized steel ASI 1015, 1030 and 1045. Okay. For these, Leroy has done experimental results for the void growth, and we use that to propose a damage growth law, which was originally proposed by Dhar et al. In 1995, and this is given by equation number 20, d dot equal to C d, which is a constant time rate of equivalent plastic strain, plus A 1 plus A 2 d into the dissipative part of thermodynamic force corresponding to damage into epsilon dot equivalent plastic equivalent. Okay. Here this equivalent rate of equivalent plastic strain rate is nothing but root over 2 by 3 epsilon dot equivalent P I j epsilon dot P L I j. Okay. So, this quantity epsilon dot P L I j is the plastic part of the strain rate tensor, this where this is given by 1 by 2 the gradient of the symmetric part of the velocity gradient tensor. Okay. So, V I is the velocity and comma denotes the differentiation with respect to x. Okay. So, here the coefficients C d A 1 A 2 are material constants, which are to be evaluated from the experimental results, and for which we use the results of Leroy, and this we will discuss in the coming lectures. And it is observed that the graph of area void fraction versus strain is almost linear at low strain level, but it is nonlinear at the higher values of strain. Okay. So, this is what the observation in Leroy's result. Therefore, to incorporate for this nonlinearity by taking the third term involving the product of A and product of D with the rate of equivalent plastic strain. Okay. So, you see we have this product of D with strain. Okay. So, one can add more nonlinear terms like A 3 d square, A 3 A 4 d cube, but it is observed in our case that the material under study such terms have no significant impact. Okay. Now, in equation 20, the first term represents the void nucleation, while the other two terms represent the void growth. Okay. So, now in the damage growth law, which is proposed by Lemaitre, the terms corresponding to C d and C 2 you will not find. Okay. So, this term of C d and A 2 you will not find in the damage growth law of Lemaitre. Okay. There you will only have A 1 times of minus y into epsilon dot plastic. Okay. So, with this we end today's lecture, and we have discussed what is meant by damage. In the next lecture, we will discuss the mathematical modeling of this large deformation dynamic thermoelastoplastic problem. Okay. Thank you.